So we are looking in the book, pick a test, any test, and try and find an exponent or logarithm question in your test.
I found the same one. Which number was it? I found the same one.
Oh, did you really?
And that's actually on my list of them too.
That's crazy.
That's crazy.
That's insane. Man, I don't know what happened. What the heck? I already know the answer. Do you know the answer?
I lost the problem because I'm looking for my.
Oh, I honestly have no clue what the answer is. I don't remember.
Let me see it. I'll tell you what it is.
I think it's 8.
It's 6.
It's 6.
It's 6.
Oh wait, yeah,
One,
it's
three,
6.
two.
6 times 6 is then 6.
Yes. You 1, 3, 2.
1, 3, 2. Yeah. What's that word again?
Wait, I think that's what
Log x equals 6 equals 2. Leaving x. How do you do it, Jane? Almost go 1 over 2.
1, 3, 2. So it's like. This is 1.
All right, so what did you learn?
X. 2 equals 6. 1.
There's not that many. They occasionally show up. It seems to be about one logarithm question, if that, per test, and about one exponent question per test.
You don't
And so we're going to talk about them, but we are also going to spend some time on geometry because that's the one you always ask me about. And in the balance of things, that's the one that it benefits more to study from. But looking at the perspective of we want to get everything, quick review on exponents and logs. So if I have a to the third times a to the fifth, what do we do? Add them. And so we would get a to the 3 plus 5 or a to the 8th. Everything in math, the more you can see the symmetry and the way things fit together, the less you have to memorize. And so here, with the exponents, if we were multiplying, we added those exponents. The log law or the log rule that we're using is the flip of that. If I have the log of k and I'm adding it to the log of m, as long as these are the same base, whatever that is, it ends up multiplying the insides. And so we have the log base b of k times m. And so just like here, multiplying meant we added the exponents. Remember that these are essentially exponents. That's what the whole point of logarithms are. And we're just multiplying them. And so if you can see that flip-flop back and forth, you can remember what to do with this a lot easier than just trying to memorize it cold. Same way, when we have division, what did we do?
Subtract.
We subtracted them. And so the same way, if I have the log base a of, we'll do the same thing, of 8 minus the log base a of 3, you're going to be dividing those. And it goes backwards. Doesn't work out perfectly, so we have the log base A of 8 over 3. That's okay. With logarithms, unless they are very, very, very contrived, they are likely to be ugly, ugly, ugly decimals. And that's the way it goes. Power to power.
Multiply.
We multiply these two numbers, and we have a to the 35th. Log equivalent, if I have the log, I'm just going to do common log, so leave it at just plain log. If I have the log of 3 to the 8th power, apparently I've got 3's and 8's on the brain, we can bring that down and say I want 8 log of 3. And so when you have an exponent, you can bring it down as a coefficient, which makes things a lot easier to work with. I'm hoping this is all review. Is anybody learning this cold? Because otherwise I'm going way too fast. All right. If I have a negative power,
What's your name? What is it?
if I have b to the negative 7, what is that?
1 over b to the 7.
It flips it upside down.
That's not what I thought.
Were you thinking of the fraction one? Because if we have b to the 1/6, that is the root, and it's the 6th root of b. So, negatives make things flip upside down, fractions are roots. I think that's it for the ones that are particularly convertible. Okay to erase?
Mhm.
Because otherwise we're running out of room. The other things to be aware of with the logs is, first of all, the definition and simplification of logs. So, if I have a to the x equals, I don't know, k. This is the base of our exponent, and when you convert it into a log, you essentially pull it over to the other side. And so this becomes plain x, log base, whatever our original base was, and then it's the log of our original answer. So this is the log base a of k. And so getting familiar with that way to flip in and out of the writing can be very helpful. I have a total of about 4 or 5 examples from the book, and that's literally what I could find by flipping through the entire book. But you'll see very quickly that in general, they tend to be very surface level, easy questions. And then every once in a while, number 58 or 59 will be a doozy. And so that's what we're fighting with on this. There's an element of, you're probably going to be fine, but probably doesn't take into account that one time they throw a crazy problem at you. So, what was the one that you found? It was the pretty basic one. So we have the log base x of 36 equals 2. So, this one, probably easiest to solve using this relationship. Easiest way to see it. So, log x of 36 equals 2, or log base x of 36 equals 2. If I rewrite this as an exponent, what do I get?
X squared equals 36.
Which makes x 6. That is something to remind you of. What happens if you type log, we're going to go with the common log, so log base 10 of negative 5. What does your calculator do?
Doesn't work.
Doesn't work. Why?
Can't take log of a negative number.
You can't take a log of a negative number. And again, this is because of this rewrite thing. There does not exist 10 to any power that will give us a negative number. If we go 10 to a negative number, we get 1 over that number. If we go 10 to a decimal, we get a root. If we go 10 to a positive number, we get positive number. But there is no power that's going to give us a negative. So logs of negatives are a no-go, do not exist. And so that one is a good fundamental bit to be aware of. What was my other basic easy one? I saved pictures. So this one wants the log base 4 of 64. So, do you just recognize the 64, or do you know how you're getting it?
64 equals x to the 4.
I know I'm getting it 'cause it's, if you do 4 to the third power, it'd be 64.
Yeah.
16 times 4.
Yeah, so if you know 16 times 4 and you can break the 16 up, then we have 4 to the third power log base 4. When these match, they cancel out, leaving just the 3 behind. Or you can rewrite it as 4 to the x equals 64 and solve from there. It depends on how you see that problem, but there are other problems coming up where you're still dealing with the equation, and so it works a little bit better to be able to do that. And so as long as you can do that and replace it, you're good. All right. So,
Wait,
yes, there are different bases in there. Like I said, occasionally one at the end throws a loop. Give yourself at least 3 minutes. See what you can get, even if it's not the final answer. What progress can you make? first question, did you get the first step and combine these two into log base 3 of 144 equals log base 5 of x? Got that far? What does log base 3 of 144 simplify to?
Nothing clean.
In that case, I might have messed up. That's what I get for trying to write it.
I think so.
Oh, because I've got the 2's in there, darn it. My fault. Should have been 81. That's 27 and 3. So my fault. 4. So from there, it gets a lot easier when I get the right numbers in. So 4.
Was I right? I was. I'm so smart.
It can be a very big number, that is okay. Alright, what did you get in?
625.
625. So let's go back to my other messy thing. If I have the log base 3 of 144, how do we get that out of the calculator? Do you guys remember how to approximate change of base formula?
Isn't it log 144 divided by log 3?
Yes. So you can use either the common log or the natural log. Technically, you could use any of the other ones, but switching into other bases for that one doesn't help particularly much. And so we could say, okay, the log of 144 divided by the log of 3, and that you can run through the calculator. And so if you do need to approximate a number, that is how you do it. I just remember the base goes in the bottom, and that's how to keep track of setting that up. All right. I apologize. I thought I had contrived the question better. All right. This one is literally question 59. So it says, if log base A of x is equal to s, and log base A of y is equal to t, then log base A of xy squared equals what? And so now we've gone full symbol, no numbers. What can we do to manipulate this one?
There is a number.
Oh, the squared?
Is that an S?
That's an S.
Oh.
We have S, we have T, we have Y, we have X, we have base A throughout. There is a squared, but that's about the only thing we've got for numbers.
We should change that to a W. I'm gonna use a W.
You think it looks like a 5?
Yeah.
I thought it was a
Ah,
Yeah, I thought it was a 5.
Well, I know we've got the little cross pieces for Z. I don't know how to make it. So it's a very basic question, but it's a real question. Should I be starting with these two pieces or starting from this one? Where did you begin? These two or that one?
I started with the one in the end.
I agree.
I did S plus T. In my brain, because it's log of A and X and log of A and Y.
Mm-hmm.
So I took, and since they're combined multiplying, that also means that is log A of X plus log A of Y.
Almost. We have to deal with the two first before we can do that. And so we're gonna pull this down and say, okay, we have 2 log A of X and Y. And now we can split this into plus and plus, but the 2's are gonna stay. So we have 2 log A of X plus 2 log A of Y. And so the fact that that 2 splits and goes to both pieces is probably the trickiest part of this problem for me.
Could you distribute it to the X and Y and just have log A of X squared, Y squared? Would that be
Yeah,
easier?
okay, if you saw it that way, that would also work.
Like just memory wise?
Yeah. And so he was saying, well, if X and Y are both being squared, this is X squared and Y squared, so I could have log of X squared plus log of Y squared. But still, in order to be using these, you still have to bring that 2 to the front. But I agree, both work. All right, so now, substitution. Log AX, we have 2S. I'm making sure that my S's are very swirly. And then 2 log AY, 2 T.
That's close.
So, interestingly enough, this is not one of the options they give us. The final thing is ever so slightly different. They have 2 S plus T. So, dust off your Algebra 1, acknowledge that that's still the same thing. All right. That's about it for logarithms. Like I said, I went through lots of tests trying to look for what they have. Logarithms aren't even mentioned in that ACT Prep Plus book. They're not there. Some of them show up in the ACT 36, which is where I got that problem that had the 3 and the 5 if I hadn't miscopied it. And then this one was a problem 59 on a random test. But other than that, it's like log base 3 of 36 or whatever that one was. And so be aware, try your best, be familiar, but don't let it eat up your brain power. It's that balancing act. If you are trying for the 36 and you have everything else down cold, absolutely study logarithms. If you are trying for a 33 and you're still feeling iffy about the geometry. All right. So, these ones I printed off because they're hard for me to write out, so I'm going to show it to the cameras. And then I can read it to you guys. And it says, The three statements below are true for the elements of the sets A, B, C, and D. A, B, C, and D. So this is the true geometry in the logic sense. There's not a whole lot of these. Frequently they just go for the triangles and the circles, but the logic still shows up. So it gives you three conditions. It says all elements of A are elements of B. Do you have any idea how to graphically organize this?
So all elements of A are also elements of B.
All elements of A are elements of B. Okay,
Just put A in a circle surrounded.
yeah. If B is everything in here, A is entirely inside B. It can't be overlapping a little bit. Everything that's in A is also in the circle B. So our second condition is all elements of C are elements of D. And so for right now, I'm doing the same thing. We have D and C is contained inside of it. We might need to erase or change this because our third condition is going to tell us how these two sets interact. But right now, all elements of A are part of B, all elements of C are part of D. And our final condition is no elements of D are elements of B. Is that true as I've drawn it? Yeah, there's no overlap, and so we can stick with that. All three things are true according to this drawing. So the next question is, which of the following statements must be true? All the elements of A are elements of C. True or false?
False.
Very false. Not possible at all, let alone all of them. All elements of B are elements of D. Now, no overlap again. All elements of C are elements of B, as in boy. Now, all elements of A are elements of B. Yeah, that's what we've got. And then the final one says no elements. Oh, I said all. That's my fault. It was no elements of A or elements of B, so that's wrong. Reading comprehension. That's in the next class, right? But the final one is no elements of A or elements of C. And that one is true. So, what did we learn from that?
Read the
Other than
words correctly.
Other than I'm fallible, read them correctly. Finish reading them. Even if you say, oh, that one's right, finish it, because I got to the next one, I'm like, well, that one's right too. So looking at those two, which one did I read wrong, or which one did I do wrong? And so it's good to finish the question, even if you think you've got the answer, just to give yourself that second check. Because reading comprehension, it's a thing, even on the math test. And especially when you're in that I gotta go mode, the chances of making mistakes can go up. So these are called Venn diagrams, even though they're not the beautiful overlapping circles that you remember from compare and contrast elementary. But they do help you to organize those a whole lot better than all elements of this or elements of that, and you're just trying to hold the words in your head. All right. So this one is a random one, but I liked it. So it says, for all real values of x, which of the following equations is true? And so it gives us sine 7x plus the cosine of 7x equals 7. The sine of 7x plus the cosine of 7x equals 1. 7 sine of 7x plus 7 cosine of 7x equals 14, sine squared of 7x plus the cosine squared of 7x equals 7, or the sine squared of 7x plus the cosine. So, the first question is, have you seen this before? It's
Yeah.
one of the ones that, not really Algebra 2 so much as pre-calc. If you were guessing with your gut and you didn't know, so if you know, don't answer yet, but if you were guessing with your gut, what do you think is the right answer?
One of the last two.
The last two? Okay, so you acknowledge, you know, we're looking for something with sine squared and cosine squared. The identity that we're going back to is the idea that sine squared of something plus the cosine squared of that same thing is equal to 1. So, which of these two should it be? Yeah. Four. Last one.
Wait,
Last one.
it's the last one?
It's the last one.
I told you.
Identities. I
So
tell
it
you.
doesn't matter what number is in
It doesn't matter what number, because I could say, okay,
Hold it.
x equals 7y.
Hold it.
Because if you divide it back over,
If we plug it in, taking the sine and cosine never get past 1. They're those oscillating functions that always bounce around between positive and negative 1. And so it doesn't matter what they are, they will always be those decimals, and then it will always go back to 1. Sure, if we had 7 sine squared of 7x and we had 7 cosine squared of 7 squared, that would make 7, but it doesn't work like that without it. So, again, it's interesting to try and guess exactly what the ACT is testing. In general, it seems to be through Algebra 2, but then it'll throw something at this like, that's a pre-calc problem. So I don't know what they feel they are testing, because if they wanted to do pre-calc, this should show up a lot more, and so it's just kind of random that it was there, but I wanted you to be aware that it might happen. We are making good time. All right, so last one. Again, technically geometry, but much more in the logic section of geometry than the measurement, but it's talking about triangles now at least. So that is our question. That's our question. And it says, Jamie claims if a triangle is in set A, then it is not isosceles. Later, Jamie discovers that triangle MNP is a counterexample proving this claim false. Which of the following statements must be true about triangle MNP? So, the initial claim says that we have a set A, and over here we have the isosceles triangles. Spelling isosceles is the hardest thing that I do. So, the initial claim is that if it's in set A, it's not isosceles. There's no overlap between these two groups. So, he later discovers a counterexample, something that makes that statement wrong. So, what conditions would have to be met in order to have a counterexample? What sort of triangle would we need in order for it to be a counterexample? It looks like I'm drawing a Halloween face on the video.
Would it be maybe like an obtuse triangle?
Equilateral.
Scalene. Or right angle.
You're trying too hard. So,
Another
counterexample
triangle.
is something that meets the first condition, but doesn't meet the second.
A
And
small-
so his original claim was, if it's in triangle A, or if it's in set A, then it's not isosceles. And so in order to be a counterexample, to prove that statement wrong, to say there does have to be an overlap between these two, is there has to be an isosceles triangle that's also in set A. A counterexample is, that's wrong, because look, this one is wrong. The classic one says that all prime numbers are odd. In general, yeah, the prime numbers are odd, but there is one number that is the counterexample to that statement.
3.
2. Because all prime numbers are odd.
Oh.
We need the counterexample that says it's not odd.
I've
It's
seen.
the one prime number that's not. And so counterexamples are all about, well, yeah, I met that condition that you asked for, but look, I broke it. It doesn't have to happen this way. And so counterexamples are about the one thing that says, that doesn't work. All and never are very powerful math statements. And you're always trying to see if you can break it. All right. That is the last of the extra weird stuff that I planned for today. You ready to go back to plain geometry?
I have a question.
Yes.
What is scalene and what is isosceles?
Okay. We'll talk about geometry.
That's
So,
a good question.
geometry is the way to, or scalene, isosceles, equilateral are all ways to talk about triangles according to their sides. And so, scalene, the classic one is a right triangle, just because, but it could be anything. Scalene just means that all three sides are different. None of those sides are going to be congruent to each other. So scalene, all different. Isosceles is that two sides are the same. The third side may or may not be the same. It's not limited to that, but two sides have to be the same. And then equilateral, that one should be familiar.
All sides.
All the sides are the same. So, with this isosceles triangle, or rather down here, so triangles by angle, we can have a right triangle, which you are very familiar with. We could have an obtuse triangle, where that's bigger than 90. Or we could have an acute triangle where everything is smaller than 90. These are not set in stone. For instance, isosceles could be an acute triangle, or it could be an obtuse triangle. Just because it has two sides the same, there's still a range of possible angles to go with it. Just because it's a right triangle, they could be all different, or it could be isosceles with two sides the same. If it's equilateral, however, it's also equiangular. And the extension from that is the idea that equal sides in a triangle make equal angles. And so when we have this isosceles triangle, these angles down here at the bottom are called the base angles, and they're also the same. And if all three sides are different, all three angles are also different. And so within a single triangle, same sides makes the same size angles. And interestingly enough, the bigger the angle, the longer the side across from it. And so that also shows up. So those are the categories. Isosceles is the one that is probably most weird. What goes on? How does that work? So isosceles, two sides are the same. If the two sides are the same, we can use those angles. Let's build off of that. So if this is an isosceles triangle and this is 50, what's x? Yeah, because triangles add up to 180 degrees. If this is 50, this is also 50. 50 and 50 make 100, leaving 80 behind for that top angle. All right. Excellent question. Any other geometry stuff that I should clarify?
If an isosceles only has to have two sides equal, but it can have three sides equal, how do you know if it's an isosceles or an equilateral triangle?
Usually they tell you.
Okay.
If they tell you isosceles, you can only work with this piece of information. But what if they told you it was isosceles and then they told you that this was 60 degrees? Well, if this is 60, this is 60. If this is 60, that's 60. All the angles are the same. Oh, look, it is equilateral. They told me isosceles, they told me an angle to work with, and then I was able to get the rest of it.
Jade, when you turn 21, maybe you up.
Yeah, right.
All right.
Because you're at 21. You have to.
No, not.
Keisha know.
Sure he did.
No, he did. I asked him about it and he said, I didn't think about that.
All right.
I asked him.
This one is not geometry, but
Oh, he
just wanted to check in because it's one of the ones that, frankly, I forget if I don't refresh from time to time. If we have the equation y equals 3x minus 12, and we have 2x minus 6, what would be the vertical asymptote?
3/2.
You sure?
Yeah.
That would be the horizontal.
Really?
Mhm.
LOL.
Oh, that's right. Never mind, it's 3.
LOL. Jade, maybe stop talking.
It is 3.
And it's on top, yeah.
So vertical asymptotes happen at divide by 0 errors. And so vertical asymptotes are just what makes this 0. Versus horizontal, so vertical asymptotes divide by 0 error. Versus horizontal it's kind of like the at infinity. And so, if you're feeling uncertain, the easy way to double check your answer is to throw in a million. 3 times a million minus 12, still basically 3 million. 2 times a million minus 6, still basically 2 million. 3 million divided by 2 million, 3 halves. And so, if you are looking for the horizontal, you can throw a really big number. In general, if this was just a number, dividing by a huge number, you're going to go to 0. And if it was x squared, you'd be going to the line y equals x, or in this case, 3x over 2. But then it would have that slanty horizontal thing. But just throw a big number at it to find the horizontal. Verticals happen at divide by 0 errors. So again, I haven't taught that particular class in many, many years, so it's good to keep the rust off. Alright. So, more logic-y stuff. For every pair of numbers x and y, such that x times y equals 0, and x over y equals 0, which statement is true? So, before I write the options, anything that you can generate,
X is 0.
okay, x has to equal 0. How about y?
Y can't be 0.
Y can't be 0. And that is the exact answer you've got in the multiple choice. And so again, the better you can generate that answer before you try and go hunting for it, the more confident you are that yes, this is the right answer. So, in order to multiply to 0, one of those factors has to be 0. That was that fundamental part of solving quadratics. In order for this to be true, we cannot be dividing by 0. So y can't be 0, we absolutely need a 0, so x has to be. And that's the logic that's going on in that one. All right. This one is very much a geometry problem, but also a math problem. So, it says the diameter of one circle is 12 inches. The diameter of the second circle is 25% longer. To the nearest square inch, how much larger?
What's the dashes?
Oh, ditto marks.
It's like saying like instead of having to write it.
So diameter of second circle.
Instead of having to write it all out again.
A apparently we have gotten too far from that because everybody's used to being able to just copy and paste in computers nowadays. So the diameter of the one circle is 12 inches, the diameter of the second circle is 25% longer.
I understand now. Sorry it took me a little bit.
I do not mind asking questions, even if they're about archaic secretary marks.
Oh. That's what I got too. Totally what I got. My head math is great.
Wait, so 12. Where's your 1.25? Oh, because it's 1.25 times longer. Times 12.
It was 12 inches.
So, that's how much more larger is it?
I was wrong.
Huh?
No, it's not. It's simply way more complicated than that.
I'm hearing lots of good thoughts, but not quite sure what to do with it. So, we're looking to the nearest square inch. How much larger is the second circle? In order to find that, we need to be comparing the areas of those two circles. So, how do we find the area of our first circle?
You find how long the diameter is first.
Well, they told us the diameter is 12.
Pi r squared.
Oh, the first one, sorry. I thought you were gonna say
Yeah, so for the first one, we have pi r squared. What's r? 6. So we have 6 times pi,
I did it in my head.
And 6 squared. We have 36 pi. Eventually, we're going to have to round to that nearest whole inch, but for now I'm leaving it in terms of pi to eliminate rounding errors. So, what is our second diameter?
7.5 pi squared.
15.
So 15 is the diameter, have to go back to the radius, so 7.5. I understand what you mean, but be careful with entering it. We don't want 7.5 pi squared. We want the squared to be on our radius. So
That's what I meant.
7.5 squared pi. Yes. Like I said, I think you were right, just to make sure. So, which one's going to be bigger?
bigger circle.
The bigger circle, the bottom one. So I would take 7.5 squared times pi minus 36 times pi. And look at that in my calculator. You do have to tell it to approximate, so if you've got fancy things turned on where your calculator leaves it in terms of pi, make sure you use the approximate button, because they want to the nearest square inch we have to round. So what are you getting?
63.6.
Which rounded up to
64.
64.
I didn't do much fun. I'm so tired. I'm sorry. This is what I do when I'm tired.
Alright, last one, and then
I know.
you are done. This falls into the graphing of circles,
I'm just trying to keep myself awake.
but it's the most complex of those that I see.
So I'll be up.
It's still not bad, it's just weird. So we have one circle that is x squared plus y squared equals 25. And we have another circle that is x squared plus y squared equals 4. And we've got a graph where here is our big circle going out to 5. And here is a smaller circle going to 2. And there is an ellipse going to the top and the bottom. Bad drawing, but you got the idea. So what will the equation of that ellipse be?
Is it like, the regular equation is like x minus h over 2 squared plus y minus k over 2 squared, right? Or is that,
Not over 2, you're really close. So,
oh yeah, yeah, over b.
over a squared over b squared.
So close.
We don't have to do that minus or plus because we have it centered at the origin, and so it's just x squared and y squared. What is this all equal to? Do you remember what an ellipse will equal to? 1, good. So this A and B is about the wobble, how far the change is. These ones could actually be written as ellipses if we just divided by 25, and then this was equal to 1. A circle is a specialized ellipse. And so again, the more you can make the connection between those two, the easier understanding that formula goes. So, in the x direction, how much am I wobbling? 5. And so this a squared is the same 25 as that big circle. How much is it wobbling up and down?
2.
Well, technically 4, but 2 radius. And so 2 squared gives us 4. And that would be your ellipse equation.
That's crazy.
Probably not close at all, but.
Wow,
How do you do
it's crazy.
So,
Sorry.
again,
You were close to something, but I don't remember what.
What was my equation that I said? Like, do you know what equation that's for? Cause like,
the divide by 2 sounds like you're averaging something, and I don't know what that
The
is.
x minus h and the x minus k part sounded super familiar from like pre-calc though.
yeah.
The minus h minus k is true for any transformation. You can use it on a squared, you can use it on a cube root, you can use it on a log function. You can use that on anything to literally pick the graph up and put it anywhere you need to.
Time's up.
Time's up.
No more math.
But this,
Oh, yeah.
And since the center's at that origin,
I was passing it out.
Okay.
that's.
Sorry, today just
So I was
been.
going somewhere with it.
Yeah, you were
I was
right.
just like.
Today was way too long.